A time series is a sequence of observation taken sequentially over time. For example, a monthly sequence of the quantity of goods shipped from a factory, a weekly series of number of road accidents, daily rainfall amounts, and hourly observation made, for instance, during the chemical process. Examples of time series abound in fields such as economics, business, engineering, natural sciences, and social sciences. Time series data in its analysis is increasingly important due to the massive production of data. As continuous monitoring and data collection become more and more common, the need for competent time series analysis with both statistical and machine learning technique will increase. And we will study and use a broad range of time series techniques that are useful for analyzing and predicting human behavior and scientific phenomena. Let's look at time series definition. Time series analysis is the method of extracting meaningful summary and statistical information from points that are arranged in chronological order. And it is done to diagnose past behavior as well as to predict future behavior. Time series analysis often comes down to the question of causality. How did past influence the future? A variety of disciplines contributed to the development of time series analysis. Let's go back to the 17th century when John Grant undertook a study of the death records that had been kept in London since the early 16th century. And in doing so, he originated the discipline of demography, study of population. In 1662, he published a book, Natural Political Observations Made Upon Bills of Mortality. The time series made its way to medicine when the first practical electrocardiogram, a study that can diagnose cardiac condition, was invented. In 1924, electroencephalogram was introduced, and its technique that measures impulses in brain. In the 21st century, we see development of wearable sensors. This is a great way to collect longitudinal data about healthy and alien population. And of course, the 21st century time series data is different from the last century. First of all, the previous data was measured exclusively on sick people, and secondly, it was limited in access. Let's look at another application of time series, weather. Predicting the weather has been an interest since ancient time. And the Greek philosopher Aristotle investigated weather in his treatise, Meteorology, and he developed ideas about causes and sequencings of the weather, and that remained dominant until the Renaissance. Of course, at that time, the scientists began to collect weather-related data with the help of newly invented instruments, barometer, for instance, to measure state of the atmosphere. And they could record time series now at daily, even hourly interval. Following that, a greater formalization and infrastructure for weather recording came in 1850 when Robert Fitzroy was appointed the head of new British government department to record and publish weather-related data for sailors. And he established the custom of printing weather forecasts in newspaper. The first forecasts were in fact printed in the Times of London. And we can say that Fitzroy is now celebrated as the father of forecasting. Let's look at another application, astronomy. Astronomy has always relied heavily on plotting objects, measurements over time. And as an example of the long history, consider that sunspot time series, the famous sunspot time series, were recorded in ancient China as early as 800 BC. Sunspot data collection became one of the most well-recorded natural phenomena. Statistical analysis of time series data and forecasting have a long history. The foundation began in the late 19th century with the invention of regression analysis and correlation coefficient concept. We can say that the beginning of modern time series started in 1927 when Udny Yu invented autoregressive technique, AR. This is the model where the past value has an effect on current values. Using pendulum fluctuation as a sample, he observed that the periodicity can be affected not only by superimposed fluctuation, but also by random disturbances, errors. And he concluded that there's a need to include noise in the model. Disturbance will always arise if the value of the variable is affected by external circumstance, and oscillatory variation with time is wholly or partly self-determined, owing to the value of the variable at any one time being a function of the immediately preceding values. He used the proposed model to predict the annual number of sunspots. So the next value was based on the weighted sum of previous observations. And for the half-century following Yu, the time series paradigm was a linear model driven by noise. It's important for us to understand that after developing this concept of autoregressive sequences, the modeling of time series was considered to be of a different character than other statistical modeling problems. To remove periodic fluctuation, for example, those fluctuations can be due to seasonality, right? So to remove periodic fluctuation, moving average was introduced. Development of the moving average as a technique for smoothing periodic data points dates back to 1901. 1901, the mathematician Reginald Hooker introduced a method of isolating short-term oscillation by correlating deviation from a moving average. This moving or instantaneous average was calculated as an average of all observations over an entire period of cyclical movement. And he used the term trend to describe the curve or line representing the successive moving averages. The trend showed the direction in which the variable is really moving when the oscillations are disregarded. Now let's look at decomposition of time series. First of all, the autoregressive and moving average model was developed in the 1930s when Hermann Wald studied the one-step prediction of a time series by the projection of a time series x at the time t on preceding values. And it was done by the linear least square estimation of x at the time t, x at the time t minus 1, etc. This direct approach yielded what came to be known as a Wald decomposition. So decomposition of x at time t into the sum of random non-deterministic component. We can call it a one-sided moving average of white noise, and a deterministic component for which there's an exact linear predictor. So we have linear model and a random noise. Wald decomposition led to the concept of ARMA. What is ARMA model? So the general ARMA model was described in a 1951 thesis of Peter Whittle, Hypothesis Testing in Time Series Analysis. And it was popularized in 1970 book by George Box and Jenkins. Autoregressive moving average model, ARMA, provides a description of a stationary stochastic process. Recall that stochastic means random, and it describes in terms of two polynomial, two entities, one for the autoregression, AR, and the second for moving average, MA. So we have on one side a linear combination of past values of the variable, and on the other hand we have a linear combination of error terms currently and in the past. Given a time series of data x at a time t, the ARMA model is a tool for understanding and perhaps predicting future value in the series. So the AR part involves regressing the variable on its own lagged means past values. The MA part involves modeling the error term as a linear combination of terms occurring contemporarily and at the various times in the past. And typically, this model refers ARMA PQ, where P stands for the order of AR and Q stands for the order of MA component. George Box and Jenkins also introduced the term ARIMA, A-R-I-M-A model, and Box-Jenkins method. So the I stands for integrated, and that indicates that data value has been replaced with a difference between their values and the previous values. And the purpose of each of these features is to make the model fit data as well as possible. And the general methodology suggested by Box and Jenkins for applying ARIMA model to time series analysis and forecasting has come to be known as the Box-Jenkins methodology or approach for time series forecasting. So the process where it generates the time series approximated using ARMA model if it is stationary or ARIMA model if it's a non-stationary. And finally, the advances in computing facilities and methods have had a great, profound impact on time series analysis. And we can name many important developments. For example, outlier detection, which became an essential part of model diagnostics. Kalman filter. Kalman filtering was introduced into time series analysis to evaluate efficiently the exact Gaussian likelihood function and to handle also missing observations. Another technical advance is the use of MCMC, Markov Chain Monte Carlo method. This method led to increasing use of simulation methods in time series analysis, which was not possible in the past.